Hello and welcome to Through the Telescope, the podcast that puts the lens on astronomy. I'm Rose Waugh and I'm an astrophysicist and science communicator.
And I'm Elliott Bruce, and I'm neither of those things, but I'll be trying to find out why we should even care about astronomy. We'll be exploring some of the big topics in the field in little manageable pieces and have some fun along the way.
So, whether you know your red giants from your red shifts, or you're not quite sure what the difference between astronomy and astrology actually is, join us as we launch ourselves into the cosmos and try not to burn up on re-entry. Through the Telescope is sponsored by Pick Astro, the astronomy and astrophotography image sharing app, dedicated to your images of the cosmos no matter what stage you are on your journey around the universe. No ads, spam, or fake accounts.
So, today we're talking about how we classify stars.
Yes, we are.
We talked a little bit about this previously. You talked about the wonderful system of classifying stars, or maybe a system, I don't know. But you're going to go into that in more depth today. So, how do we classify stars?
Well, like you suggested, you can classify them in lots of different ways. But a common way is to use their spectra, which is looking at all of the different kinds of light that the star gives out.
So is that like visible light, like all the different colours, or are we talking like X-rays, gamma rays?
Yeah, so we're talking everything.
Everything.
So, yeah, light is an electromagnetic wave.
Mm-hmm. And
just like waves on water or anything else, they can have different wavelengths. So that's the distance, just means how close or not the peaks of your waves are together. I'm aware that you know what wavelength is. But
yes. No, that's fine.
And yeah, they come. Some of these wavelengths are visible to us, the visible light, and these come in all different colours. So red light has the biggest wavelength, and blue light has the smallest wavelength.
Yeah, and the shorter the wavelength, the higher the energy. So blue is high energy, and it's close to UV, whereas red is low energy, and it's close to infrared.
Yes.
For instance.
Yeah, so you took the words out of my mouth there. So.
Oh, great.
I was going to say wavelengths that you couldn't see would include things like UV, which I think is probably the one that most people are most familiar with, because we're aware that it's not good for our skin.
Yeah.
Because it has lots of energy.
If you kept on going, you'd end
end
up
of the spectrum.
X-rays and gamma rays, which are also not great for you. Although I think when you get to gamma rays, they start to become okay, right? Because they just go straight through you.
Eventually, not a big deal anymore. Yeah.
Yeah. Whereas the other end, IR. I mean, people are happy with infrared, night vision, not night vision.
IR
that's different,
therapy,
isn't it?
Your hot water bottle, whatever.
Yeah, and then further down you got, I guess, radio. Radio waves.
Yeah.
It's
which people are very familiar with on a day-to-day level, even if they're not aware that that's a thing. Although I suppose no one listens to radio over the airwaves these days. Everyone probably listens to it on their broadband. But yeah. And they're all different types of light. So
okay, yeah. So do we then look at like this is like an X-ray star, or is it more like this is a bluer star, or is it just like all of these things together?
Yeah. So the spectra is all the different kinds of light that the star gives out.
Okay.
So all of the light types, if you like, that we just talked about. So, we would call that in general a colour anyway, including stuff that you couldn't see. And looking at all of the light that is emitted by the star, all the different colours, we can then sort the stars that are similar to each other into groups. And because the different colours that we see relate to the elements that are there, or the molecules or whatever present in the object that you're looking at, like a star, you can kind of tell stuff about the object that you're looking at. You know, you can tell what it's made of and things like that, for instance.
I guess we talked a bit about that in the exoplanets episode. We're talking about going through atmospheres, I think.
Yeah, exactly. So, I mean, some people might have seen these pictures before. If you go onto Google and you type in like stellar spectroscopy or stellar spectrum or something, some of the pictures you get kind of look like a barcode.
Yes.
Of all the different colours that you could have, and there are some bits that are omitted because that particular thing isn't made on that star or whatever. So you can then group your stars based on this thing, and this technique is called spectroscopy, which is a term I'm sure you're quite familiar with as a chemist, because it's...
Yeah, I mean, the spectra you're then talking about, which is now going to be more confusing because there's spectra and spectra, but when you're talking about the individual lines like a barcode, that's then looking at sort of energy levels of atoms and molecules and sort of quantum theory and sort of, physical chemistry. Yeah.
Again, a link between astronomy and chemistry there, which is nice. Yeah.
So we just... Is there ever like a sort of, well, this is red, but there's lots of X-rays? Or like, so that's one type? Or is it sort of, how do we sort of look at the whole spectrum? Is it just looking at those lines, those barcodes, like you say? Or is it like a sort of hump?
You can look at, you could make a plot that's intensity, brightness, if you like, on the vertical axis, and then, wavelength or frequency, which is another way of really talking about wavelength, really, let's be honest, on the horizontal axis, and you would get a curve that looks a certain way. And for different stars, this curve would look slightly different. So it generally has the same kind of shape, but it moves a bit on your plot.
Right. So then you classify it based kind of on where the peak in your curve is or something like that.
Some people might be familiar with the idea of black body radiation.
Okay.
Black body curves. And the idea that if something was a perfectly emitting object of light, any energy that it had, it radiated away, all of it, you'd get a certain kind of plot.
Okay.
I'm sure you have come across this yourself.
Yeah.
You can model stars using black body radiation.
Okay.
And in some ways it does remarkably well for how clearly crude a model that is. And the kind of plot that you would get depends on the temperature.
Right, okay.
Of your object, in this case the star.
Yes.
So the peak is, amongst other things, dependent on the temperature.
Okay. So we can look at the colours that we see from the stars in different ways, and then that then gives us our category, does it? Is that how we're then classifying them?
Yeah, so if you look at a star that's very white, for example, it's very hot.
Okay.
If you think of your classic iron fire poker.
Oh, right, yeah.
It's white hot.
Yeah.
When it gets really hot. And actually red is the
cooler
least hot, but still hot. By the point of it glowing. It's obviously, if your fire poker is red, don't touch it. It's going to be hot. But the point is, it's less hot than if it was glowing white.
Yes.
So, the same is true with stars. So, yeah, the colour relates to the temperature.
Okay.
Or you might hear it said in a more kind of fancy way in astronomy, in terms of colour is a proxy for temperature.
Right, okay.
So
Because
you can look at the colour and you can infer. You can make a plot if you wanted of something and then plot it against colour of your star. And that's equivalent to temperature.
Okay, right, yeah, you don't need to worry about...
It's a proxy variable.
Yeah,
Yeah.
I see. And you can also measure that, and you don't need to worry about it anymore.
Yes, whereas trying to measure the actual temperature of an object billions of miles away from you is...
And it's just going to be based on the assumption this is what the light is, so... Okay, so then do we then sort of dump it into, well, this is a white hot poker star, and this is a red hot poker star. There are two classes of stars. Is that kind of the gist of it? Or have we got more?
Once upon a time, kind of. So, a long time ago, not that long ago, it was like the 1800s.
Okay.
But there were 3 classes of stars, which they helpfully called Class 1, Class 2, and Class 3.
That's handy.
Yeah. So Class 1 were the white/blue stars.
Okay, so
white and blue ones. The Class 2 were the yellow stars, which it turns out are pretty metallic.
And by metallic we mean
anything that is
not hydrogen or helium.
Yeah.
So
I just thought I'd bring that up again for our own trauma response. Yeah. Class 3 were the kind of orangey stars.
Okay. So we're getting
and they
cooler.
Have more kind of complex spectra.
So we've got white, yellow, orange.
Yes.
So that's getting cooler as we go from the first, what did you say, Class 1 to Class 3. Okay.
Yeah. And then, however long later, as happens in a lot of science, but it was really common in astronomy, these classes that had been made up kind of arbitrarily from stars we just happened to have looked at weren't enough.
Right.
So we then ended up with Class 4 and Class 5 being added.
Okay.
And Class 4 were the red ones.
So that's cooler again, I'm guessing.
And that means that carbon is present. Really.
Okay.
And then Class 5 were kind of funny ones where...
There's always one. Is Class 5 the class that doesn't fit into Classes 1 to 4?
Yes, exactly. So the spectra that we have talked about already can have emission lines or absorption lines.
Right.
So emission lines are when your star is emitting something.
Mm-hmm.
Like you say, that chemical is present, that element is present, and the heating and cooling, or the exciting and de-exciting of that chemical leads to light of a certain wavelengths being emitted. Absorption lines are when you don't see light from a particular thing.
Yeah.
A particular chemical or whatever. So if you looked at the light, you could draw your barcode, if you like, and you could have it with your bars being coloured in because that light is present, or you could have them being black and everything else being coloured in, if you see what I mean.
You can either have a rainbow and then black marks drawn on top in certain areas where you're like, that must be hydrogen, because it equates to the energy levels of hydrogen. Or it's the opposite way around. It's like, that's whatever colour. So
So Class 5 are the ones where, oh no, we don't see the absorption lines like other stars. Right. We're seeing emission lines.
Is that we're not seeing the absorption lines? We don't know why. Let's put it into Class 5 and not think about it for a while.
Yeah, there isn't... I don't think there was that much knowledge, really, at the time. I mean...
This is the 1800s still, isn't it?
Yeah, just about, I think, if not in the very early 1900s.
Okay.
And then Wilhelmina Fleming came along.
Okay. Is this a name that we should be remembering. It's the name to mark down on our notebooks.
Yeah, I mean, you know a lot of male astronomers. You might as well learn some female ones. Well, she was one of the first Harvard computers.
Okay. I'm sensing an issue here because this is a person.
Yes.
Not Microsoft Windows computer or an Apple Mac.
No.
Other computers.
They weren't invented yet.
Okay. So this is like early 1900s, is it?
Yeah.
Okay.
Yeah, I mean, we'll come back to the Harvard computers, I'm sure, but people probably know the idea since Hidden Figures was very popular. It's the idea of getting humans to do, lots of kind of calculations and generally repetitive tasks that you would get a computer to do, if you like. Obviously, not all of them were things that like a desktop could do, but they are computing things.
They do the math.
Yeah. And she started a lot of the hard work, really, in dealing with this classification mess that was beginning. And divided the previous classes, class 1 to 5 that we talked about, into further groups.
Right.
Because she thought, this will help.
Is the end of this, is the spoiler going to be, it didn't help?
Well, she decided to give them all a letter.
Okay, so we've gone from numbers to letters.
Yeah. She decided step 1, change it from numbers, let's make it letters.
Okay.
A to N, excluding I.
Because it looks a bit like a 1?
I think maybe.
Because you don't want it to look like class I, and people are like, oh, it's a class 1 star.
I don't know the answer to that, but I've always assumed it was...
Yeah, that's fair.
For...
Also, I find I's really irritating, because if it's a capital, it's like, is that a lowercase l? Or is that,
Yes.
all of these things.
Yeah.
I is a really, depending on your type, your font.
Yep.
But yeah, fair. Okay.
And then later she added O, P, and Q. Let's try that again. Later she added O, P, and Q.
Okay.
As well. So we've got quite a lot of classes there.
That is quite a lot. That's most of the alphabet.
Yep. Then Antonia Maury came along. I hope that's how her name is pronounced.
Okay.
It's spelled Maury, for anyone who wants to look that up. And she had the advantage of better data, which is classic.
Yeah, that's why come up with a system when you can just wait a few decades?
Yeah.
It would be better.
I mean, I don't know how long she waited.
Okay.
She was also a Harvard computer. She created a system with 22 classes.
Right, so that's almost an entire alphabet at this point.
Yeah, so we've gone from 3 to 5 to most of an alphabet to pretty much the entire alphabet. Then
we're going to have to start adding on new letters. We're going to go Greek. Mm-hmm. It's going to X, Y, Z, alpha, beta, gamma.
Yeah. Well, you're not far off, to be honest.
Oh dear.
But Antonia Maury did a lot of the very important groundwork for the HR diagram, which I think deserves its own episode.
Okay.
All on its own, but...
The human resources diagram.
The Hertzsprung-Russell diagram.
Ah, that sounds like two people called Hertzsprung and Russell.
Well done. You know science.
See, I have actually heard of the Hertzsprung-Russell diagram before, but as a kid, I don't know where I heard it as a kid, but I always thought it was the Bertrand-Russell diagram.
I see. No.
He was a philosopher, maybe? But no, it's not the Bertrand-Russell diagram.
Hertzsprung.
Hertzsprung-Russell.
Mm-hmm.
Okay. So she's setting these guys up.
Yeah.
So it should almost be an Antonia... I've not heard what she's done yet, but it could have been the Antonia Maury diagram.
Probably not, but with that said, I reckon she probably got a lot... Well, she will have got a lot less credit for how much her work set up.
And I'm already guessing
than other people have got.
I'm already guessing that Hertzsprung and Russell are going to have, like, doctory positions or something, and
Yes.
she has not got doctory positions.
No,
and
she hasn't. She is a human computer. She's getting paid pretty much the same as a factory worker.
Right.
She's getting paid unskilled labour.
So I was going to say...
Anyway, we're going to come back to
Okay,
this.
we'll come back to
so,
this. Come back to human computers later. Tell me more about Antonia Maury.
She worked out that similar colours of stars have the same absorption lines in the spectra.
Okay.
So when we were talking about how different colours are related to different things,
That's
like
based on her.
It's very easy for us to have that conversation now, and it's, taught pretty early on in astro-related degrees. Not that I did an astro-related undergrad, but this was not knowledge that they had.
Yeah.
Yeah. So she was the one that did, or at least is credited for working that out, and that the spectra is dependent on temperature as well.
Which then future astronomers have been very happy with, because they need to plot wavelengths or frequency rather than having to work out the temperature themselves and plot that. So thanks to her.
Well, they would plot colour.
Okay.
Or they could, you could do temperature. You would just find a conversion. Probably.
So she's worked out that the colours of stars are related to absorption lines and that the colour is dependent on temperature.
Yeah.
So
yeah,
she's worked out a few things in a classifying
lot
of 22 classes.
Yeah.
Okay.
Then came Annie Jump Cannon.
And we now have 52 classes.
Who you might have heard of. She's more famous than the others, I would say.
Okay.
But still not famous enough.
Okay. I don't think I know the name Annie Jump Cannon. It's a pretty cool name, though, to be fair.
Yeah. Also a Harvard computer.
I'm sensing a pattern here.
Yes. Yeah, they all were. And she compiled a stellar catalogue that kind of more, or the stellar catalogue more as we know it.
Okay.
And the classification system of the Harvard system is what it's normally called.
Harvard system. So the Harvard computers, Harvard system.
Yep.
They're working at Harvard.
Yes. Yes, they are. And she, funnily enough, this isn't going to come as a surprise to you,
Okay.
wanted to make the system less complex.
Okay, so she's gone the opposite way. It's not 52, it's 12.
And she went back to Wilhelmina Fleming's work.
That was...
The letters.
How many was that? We got up to Q, was it?
Yes.
Without the I.
Without the I.
Okay.
And she was like, this is great. But actually, the order of these needs to be changed because I now know about the work of Antonia Maury.
Okay.
And all of the stuff about the colours and the spectra and the temperature from that. And so actually we've got to reorganise these.
Okay, so she's
So now instead of the alphabet, we've got O, B, A, F, G, K, M.
Well, that's less than 22.
Yeah.
But I am... Right, so this is to be consistent, as it were, with Wilhelmina Fleming's system. And it's then ordered based on some of the stuff that Antonia Maury's worked out. So, O, B, A, F, G, K, M. That's a smattering of... that. If you got that in Scrabble, you'd be
crying.
worried.
Yeah.
You got 2 vowels, I guess.
Yeah.
If anybody can work out what the best point scoring word there is, then please let us know.
Yeah. We'll send you a free print of some piece of artwork.
Foam. Got foam.
Foam, yeah? Yeah.
Fang? No, there's not an N. Jeez. Okay.
So that's what we're left with.
Right. And that's in order of colour then, is it? Which is also temperature.
Wow.
Uh-oh.
It's an order of mass.
Right.
But the temperature relates to the mass as well.
Okay.
So there's a whole lot going on.
So they
which
don't...
is maybe not surprising when you hear about how we've
much
attempted to get here.
Yeah, and how much we didn't know and how much we did know. So do they know that it's mass at this point? Does Annie Jumpkin know that it's mass, or are we still working in like
Not
temperature?
sure.
Okay.
But it's definitely thought of with everyone that I know anyway in terms of mass.
Okay. But we got it down to
That's how
7.
it's thought about.
So that's pretty
Yeah,
good. We're
so
sorted.
we're doing good. It's down to 7. And then later she thought, but though...
Oh, this is how it works out. You go from 22 and you're like, this needs to be less,
It just
and then
needs
you
to
come
be
back to the same.
more precise.
Right.
So she thought, well, I've already got letters, so let's add some numbers into it.
Okay. I guess that's better
So-
than a lowercase letter after a capital letter. Right.
So now it goes letter,
Mm-hmm.
and then some number from 0 to 9,
Okay.
where 0 is the hottest, 9 is the coolest.
Okay.
So, for example, the sun is a G2 star.
Which...
So it's
means
a G type,
Okay.
and it's 2, so it's pretty hot for a G.
Why did they pick the lower number as the hotter one?
I don't know.
I want it to be the other way around.
I mean, maybe there's some logic there, but yeah, right?
So is O the hottest or is M the hottest?
O will be the hottest.
Okay, so it goes O0 is the hottest, is it? And then M9 is the coolest.
So O stars are the very biggest stars, and they burn through their fuel really quickly because they have high gravities.
Right, so this is where the mass bit comes in.
And therefore, the temperature of the star is higher because there's a lot of pressure in the star to cause the high temperature because of the high gravity. And yeah, the high temperatures tend to speed up every reaction. I mean, you're a chemist, so I'm sure you're on board with that. So they tend to burn through their fuel pretty quickly.
I guess
because
also...
they're hot, so then their reaction happens quicker. So they don't tend to live as long. They don't live as long.
I guess also high pressure probably helps with fusion, does it? Because everything's going to be closer together, maybe. Probably at that point it starts to become a bit weird.
Yeah, I think the chemistry and
I'm not a nuclear
physics
physicist.
of these things are pretty weird environments. And they tend to be white, like white hot.
Because this is the white hot poker. Okay. High mass.
And as you go down the list, the stars get smaller and cooler. So you get down to G, that's the solar-like stars.
Okay.
K, they're a bit smaller, but they're still pretty similar to the sun, really, all in all. And then M is the M dwarfs, which are very small stars.
Oh.
And also sometimes called red dwarf stars.
Like the TV show.
Like Red Dwarf. Yeah, I put that in because I thought you would be interested to hear that.
Yeah. So are they called M dwarfs because they're small M stars, or are all M stars M dwarfs?
They're called M dwarfs because they're M type and they're small stars.
Okay, so can you get some M not dwarfs?
No.
Okay.
And as far as I'm aware, no. Which is really weird.
Because you could just call them M stars.
Yeah. But if there's one thing that I have really just learnt in the past however many years of my PhD, which is quite a long time, but we won't mention that, is that when it comes to stars and like classifying them, this mess has not been cleared up.
Right. Yes.
That's the vibe I've got from this. You know, why is it an M dwarf, but everything else is like a K star?
It's not
but
like
maybe
an O supergiant.
someone might call it a K dwarf because they can.
Like a dwarf.
You know, why call your M dwarf a red dwarf?
Oh, and they're red because they're the cooler ones. So they're a red dwarf. Okay.
You know? But then you don't call it like white massive star. Do you know what I mean?
So is this classification
know.
useful?
And some people will be like, talk about L stars, which aren't on this list.
Oh, hang on a minute.
Yeah, don't even get me started. So
right. So
it's chaos.
So
it's chaos.
When you say this is called the Harvard system, does that mean there are other systems that are like you're then saying L? Is that like the Harvard Plus or the? Do you know what I mean? Are there other ways of classifying stars that are
there
not
most
as popular?
definitely will be. I mean, that's like asking, is there another way of rearranging the elements apart from the periodic table?
And the answer is no.
But the answer is, yeah, there most definitely is, but it's
There
not
is.
necessarily sensible.
Yes.
I mean, the periodic table has been well and truly tested, so, maybe in however long there will be a different way of classifying stars. I think it's kind of unlikely, but maybe. And there will be other systems out there because you can make a system in whatever way suits you and your needs. But yeah, this feels to me like there's quite a lot of like hand wavy things.
Yeah.
Things aren't really defined very explicitly, which really upsets me.
Yeah. So also, like, if you've got like an F and G star, are there any stars that are like halfway between? I guess like an F9 and a G0, or like it could be an F9 or a G0, or is it like pretty much it's got a set boundary? So if the wavelength is like above or below.
Yeah. Does that answer your question?
Yeah. So
Yeah.
Does the classification matter? Is that, or is it sort of shorthand for I'm really into super heavy stars, so I'm into like O and B stuff. So it's helpful to search for O types and B types, say.
You mean like in the literature, or?
Yeah, just like in day-to-day like astro work, or is it? Do you not really care? Are you working on B types and G types and M types?
Yeah.
I guess is it all academic?
It's a good question. I mean, I think I get the impression that research has kind of changed quite a lot, even relatively recently, and academics used to just dabble in everything, didn't they? I mean, those people still exist, for sure, but it feels more like these days you go into a niche in your field and you kind of stay in that niche. You might it'll evolve over time, and you might at certain points change and do something quite different but with the same skills. But it kind of feels more narrow than when I look at people who have kind of, not to be like depressive, but more like at the end of their careers, and they have for quite a long time done some kind of wildly different things. It doesn't really feel so much like that now. So like, you, in many ways, if you know about stars, you know about stars, right? So in many ways your skills and your knowledge is applicable between an M star and an O star.
Yeah.
Even though one is tiny and one is huge. But actually there's quite a lot of different physics that goes on within those stars that I couldn't even comprehend until I ended up doing stellar research.
Yeah.
How different they actually are. And so you can feasibly, be someone who's like a solar physicist or a stellar physicist that works on low mass stars and never ever in your life go anywhere near stuff on high mass stars, or vice versa. So it is helpful from an academic point of view. I can go on to the archive of papers and I could search for M dwarfs, and I know that what's going to come up is going to be relevant to me, for example, or solar-like stars.
I guess also,
and so maybe in that sense the hand waviness doesn't matter. But I don't know.
as a member of the public, a Joe Bloggs type, and you're sort of vaguely aware of stars in the night sky, you're like, oh, Sirius, Polaris, they've all got names. And then I'm listening to you talking about your research, you're like, so I've just found another star in the database that I can compare my work to. It's
Which I never say, by the way.
MK473542A.
Yeah, you read out its number plate.
Yeah, and I say, sorry, what? And you're like, oh, MK472A. I very much doubt that was what I first said. But it might be quite handy if you're at a conference or in a paper already, just to be like, this is an O-type star in this place. And then you're like, oh, I know what that means as a researcher.
Yeah, it's very handy, and people do it all the time, yeah.
So I guess that's a benefit of having a classification, even if maybe it's a bit like, is there an L-type star? Is it an 09 or a 08?
It's not so much that, it's not like this. It's not like there's anything particularly wrong with the system. It's just, I think it's more, I don't know, not cultural things, very like extreme, but I don't know if it's just kind of like a leftover thing from this being not very well defined and not very well classified for such a long time. That people just are lazy with stuff. Like, why call it a red dwarf when you can call it an M dwarf?
Yeah.
Why do that?
Well, you can make popular culture references.
Like, it's just not helpful.
Yes.
I understand that there is a bit of added knowledge there, but like really not really.
Yeah.
You know what I mean?
Is it like a cultural thing? Is it like, Europeans would call it an M dwarf and Americans would call it a red dwarf, for instance? Or, you know what I mean?
I don't know.
Is it a generational thing? If you're like an 80-year-old professor emeritus?
Maybe. I don't know. I mean, within my experience, there's not been any rhyme nor reason, but it doesn't mean that there isn't a pattern there, I suppose.
So, if O's the biggest and M's the smallest, does that mean there isn't, by definition, there's not like a bigger than an O? I guess, is that like a black hole at that point? Or,
yes.
And then is there anything smaller than an M? Is that like a Jupiter? It's not a star. Or...
Yeah, not really bigger than an O, smaller than an M. You could get a brown dwarf, which is the very smallest stellar object. I say that in that I would call them a stellar object.
Okay.
Are they a star? Different people have different opinions on that. Again, we're back to hand wavy. Some people would say, yes, it's a star, but it's like a failed star. It's not like, but it's a star. Other people would be like, well, it's not a star because it doesn't make its own light. So it's not a star.
Right, yeah.
You see what I mean?
Yeah.
They're kind of a weird thing that's kind of not a star, not a Jupiter. They're their own thing.
Starry Jupiter.
Their own interesting object, but kind of a weird thing. Yeah. In fact, size-wise, they're really small. They're not any bigger than 0.075 suns.
Right.
Which is about 75 Jupiters, I think.
Okay,
so,
yeah. So I was going to say from our episode on the solar system, the sun makes up a lot, so even 0.075 solar masses is quite big.
Yeah. Well, yeah, I mean, to me, my brain does it the other way around, which is just shows how we can't deal with numbers, right?
Yes.
Because I'll go 75 Jupiters, oh, that is quite big, yeah.
Yeah.
0.075 suns, yeah, that's small.
Yeah.
I'm like, it's the same object.
Yeah. It's like you wouldn't be able to see the planet Earth if it was anywhere near the sun.
Yeah.
Yeah.
So it's just a matter of units, isn't it, really?
Yeah. So we've got OBAFGKM. I'm guessing it's not just like evenly spread. There's like, how would you say, a 7th O type, a 7th M type.
How do you know that?
I was just a guess. It doesn't. I feel like even though you've just classified it into 7 equal categories, the universe is not going to say, yeah.
No, the universe definitely does not say, yeah, that's a good idea.
Yeah. So is it like 1% O type, 99% M type? Or...
Yeah. So smaller stars are much more common, which makes sense. Yeah. Actually, in the observations, there's a little peak. Oh. So, instead of thinking of it as like an exponential decreasing as the mass gets bigger, there's like a weird little peak before your curve decreases. So it kind of goes up and then down.
What's that peak? Is it us?
Yeah, we don't really know, but lots of astronomers think it's a biasing in the data, that small stars more difficult to find because they're just not as bright.
Yes.
So they're kind of more difficult. So probably not a real feature, probably of the universe, and more a feature of our observational capabilities at the moment.
Do you think that'll change with JWST, or is that just going to sort of increase the total number of stars, but it's still seeing brighter stars? It's just that they're now further away.
Yeah, I don't know. I don't know how it really works, because presumably, if you just get a better telescope, you just see more of everything.
Yeah.
So you would need to get a telescope that sees more.
That in some ways biased the other way, as it were.
And then you need your biasings to cancel out in whatever. So, who knows?
Yeah, it's kind of interesting, isn't it? Because as a non-astroscientist, I'm quite used to the idea of you can at least pretend to have control over your experiment. But with astronomy, it's control out there, and you get what you can get.
Absolutely no control. Yeah. It's a different kind of experimenting, isn't it, really? You don't... It's literally all just observing. Like you say, you look up and you hope that what you get is helpful, and you can help yourself by knowing to look in the right places for the thing you want to see, but you've no control over seeing a particular thing.
Yeah, and you can have theories and simulations, but they're based on your observations in another way. So it's then...
They often are based on observations, yeah. It's pretty rare, especially these days, for theories to be much more kind of cold hard principles.
Yeah.
They do exist, and they have happened in the not that distant past. But often guided by observations, and observations tend to be guided by theory, so it goes both ways.
Yeah.
Which is helpful, but it's a feedback loop, and that's not always helpful.
No. So that was stellar classifications, and the perfectly logical, sensible classifications that we have to this day. It sounded like pretty much everything there, apart from the very early stuff, was based on Harvard computers. Yeah,
they did a huge amount of the work.
Which, from what you were saying about, low-paid factory worker, but with numbers, essentially. Does that mean that when you say the term Harvard computer, that sounds more like sort of human robot to me? It sounds like drudgery worker. Is that what it was like back then as a term? Do you know what I mean? Or did that have more of a... Did being a computer back then not sound like a dehumanising thing because computers didn't exist?
Yes. I think it's a bit of both, but like you say, it's nothing to do with the word computer. They performed a lot of tasks that they were often highly skilled people and underpaid, specifically women, and they were trained in astronomy and maths and physics and research, and often they had university degrees. Not all of the time, but often. And the reality is they were unable to get other jobs, similar kind of jobs, that would be better paid and have a career progression to them. And so, to some extent, I think it was they probably viewed it quite positively, because it was their opportunity to do the thing that they presumably liked and loved, were interested in, which they wouldn't otherwise get. But then at the same time, they're being paid, the same as a factory worker, despite being highly skilled people, knowing that men could make a career out of this and be their boss pretty quickly, really, in reality.
Yeah.
To some extent. So, there's always going to be a dehumanizing element there in that sense. But what they did was kind of not robotic. I think a lot of it was quite repetitive, because they took a lot of measurements of stars. They measured the brightness and the position in the sky and the colour, and they took spectra for hundreds of thousands of stars. I think it was something crazy like 220,000. Like, if you took all the plates that they had taken their observations on, because telescopes used to take pictures on plates, like cameras.
Right,
yeah. If you took all of them, it would weigh more than 1.5 tons or something, So, it was a crazy amount of work.
Yeah. And how many people, I'm guessing...
And some of that is going to be quite repetitive.
I'm guessing they don't have, 200,000 people working as human computers,
No, they don't, but this is... So... The watchful leader of the group of the Harvard computers was a guy called Edward Pickering,
right?
Who was an astronomer and famous for discovering a certain type of binary star.
Is it a Pickering binary star?
No, a spectroscopic binary star.
Okay,
if you wanted to look that up. And it's a star system that's got 2 stars in it. It's a binary system. And the stars are pretty close together, and they rotate pretty quickly.
That sounds like a right nightmare for working out which star it is. It's it looks like this star and this star together.
Yeah. Yeah.
That's a class 5.
So he wanted to classify stars.
Okay.
He also had money from a widow.
Okay.
Mrs. I can't remember her first name, but her last name was Draper.
Okay.
And she worked with her husband, who did some work on classifying stars and some other things.
Yeah.
And she worked with him, because that was often how women were allowed to do science. And he died, and so she decided that she wanted this work to continue, and she wanted his work, and presumably her own work, because it is also her work, to get published and to go somewhere after all that. So gave money and some telescopes and stuff to Edward Pickering, who was their friend, their family friend.
Okay.
To do something about this, because she couldn't do it now, because she was not allowed.
Oh, because she's now not married, so it's not her husband working. Is that kind of...
So she
can't work in her own right on the stuff.
So he decided to set up a group to do this. And because he could pay women a lot less,
Nice.
he could get a lot more of them.
Mm.
And basically, you know, we're now living in an age where there's so much data we don't know what to do with it. So like CERN or like, you know, some of the big telescopes, I'm sure that the Square Kilometre Array and other things like this will be following suit. They just observe so much stuff, and a huge amount, like 90% of the data, just gets instantly binned. Because we can't store it anywhere. We cannot deal with the amount of data.
Yeah.
So it gets filtered into, you know, is this interesting or not? Obviously, a computer is not perfect at doing that, so there could have been huge amounts of interesting things. We've just binned it.
So much stuff.
Really quite something, isn't it? But, you know, these places do their best with the technology that we have available for that to not happen, but it's bound to happen because we're just binning so much of it. And they were kind of in a similar situation.
So they're the ones deciding whether to chuck out the photos that they've taken of nothing. Is that
well, not so much that, but they were in a similar situation of just the amount of data that they needed or were collecting, depending on the project, was just so much they couldn't deal with it. They couldn't process all of it. And so his solution was get more staff.
Right. I love the idea that in, like, I don't know, was this like the 1920s or something? They're like, we've got so much stuff, we can't possibly process these 200,000 things, and then...
I mean, that was over time.
Okay, yeah. But you meet someone today, they're like, we've got over 7 quadrillion things.
Yeah.
And it's like, 200,000, that's I can go on a floppy disk, and we don't use floppy disks anymore.
Yeah, exactly. Yeah, times have changed, for sure. But
I did see a
this was how he ended up with a whole bunch of women in his lab.
See.
But, you know, I don't mean for this to have been like a depressing element of just like gender segregation and oppression, which is still very much widespread in the world. But something that I thought, as well as that kind of teaching moment from history, was quite positive, was that after Pickering died...
Don't worry, this story picks up after he dies.
Oh, no, that's not what I meant. But after he died, instead of them just bringing on another man to take over, Annie Jump-Cannon was the one who...
jumped in.
Who took over the Harvard computers.
And does she get a bigger paycheck? But not as big as him, presumably.
Don't know. I mean, gender pay differences still exist today, so...
but a lot of the time it's meant to be illegal.
Yes. It is meant to be, but...
Doesn't stop it happening, but... let's see.
But yeah,
so these are the Harvard computers. Does that mean there's, like, I don't know, the Yale computers? Do all of these observatories or whatever start going, I know, we've discovered this new thing called computers. We get a bunch of women, we don't pay them very much, and they do sums for us. And it's a miracle
it's great.
of the early 20th century.
Yes.
Soon everyone will have a computer in their house.
Yes.
Is it just Harvard?
It's not just Harvard, no. They were pretty common, so...
Women are exploited everywhere.
Again, still true to this day. So the moon landings, you know, they're very famous, the human computers at NASA.
Yeah. What's better than exploiting women, exploiting black women?
Oh, yeah. But the Greenwich Royal Observatory also practiced this, amongst other places. So, yeah, it's...
both sides of the Atlantic.
It's not just Harvard.
I see. But we don't hear about the Greenwich computers.
No, I suppose they didn't get us to the moon, so maybe they're not quite big enough for a Hollywood blockbuster movie.
No, and they didn't come up with a system that was OBAFGKM.
That sounds like a really naff radio.
Yeah.
What's the word?
I don't know, acronym, maybe? It feels like in the UK, or maybe not just the UK, but when you hear, like, sections of American things, it's like, tune into OBAFKGM Radio, your home for all your music needs.
Can confirm that is true.
Yeah.
I was 20-something years old, too old, when I learnt ABC, the ABC station.
Oh, right, yeah.
American Broadcasting Centre. I think it stands for something.
Not to be confused with the Australian Broadcasting Corporation Company.
I don't know if it's centre in America, but like...
Yeah.
Yeah. It's
not just educational videos or something.
Just for however long was like, they have a channel called ABC.
ABC.
Why are they so obsessed with letters? Like, just...
Yeah, I guess you got, is it MSNBC? Which means something. Yeah. So have you got any positive, uplifting... he died and somebody got a pay rise, maybe. And we know their name.
Yeah.
Which I think that's actually quite impressive, to be honest. Like, they're computers, but you go, I think, was it 3 different names you gave?
Yeah.
Let's give them a shout out, if you listen.
Yes. Shout out to Wilhelmina Fleming, to Antonia Mowry, and Annie Jump Cannon. All people that we should know the names of, and they did some really groundbreaking work, really underpaid, as many postdocs
Yeah.
and PhD students relate to.
So that just about wraps things up for this episode. Please, can we encourage you to subscribe to Through the Telescope wherever you find your podcasts, and if you like, you can leave us a nice positive review as well. It really helps the show, and it makes it easier for more people to find us.
Feel free to send us any comments, questions, or suggestions of things or people you'd like to hear about or from in future episodes. Or perhaps to put yourself forward to chat about your own astro research or experiences. As always, you can find us on Instagram at Through the Telescope Podcast, or you can find me at astrophysicist_Rose. You can also find us on Twitter at The Telescope Pod, and you can contact us by email at throughthetelescopepodcast@gmail.com.
And with that, we'd like to thank you very much for listening, and we look forward to seeing you again next time.
Bye.
Bye.